right, so sequence-defined structure. A key principle in protein biochemistry. Sequence will determine what structure we go into, and that'll determine what function we have. Function being also related to location. Structure and function will relate to location. Are we embedded in a hydrophobic membrane? Or are we some water-soluble globular protein? And so if we look at, we're familiar with myoglobin and hemoglobin. We already talked about it a bunch. It has, first of all, it only has alpha helices, but it has several shorter alpha helices here. It has A, B, and C are highlighted in its sequence. And what we see is there's really no more than 3 nonpolar residues in a row before we have something that has some sort of charge or polarity to it. Okay. But for our Bacteriorhodopsin, that was the pronunciation, I think. As it traverses the membrane, you can see it has almost exclusively nonpolar residues. Okay. It's also longer. What would be a reason that it's longer? Yes, Elsa.
It can reach all the way through the membrane.
It needs to be able to reach all the way through the membrane. Okay? Perfect. Is this title, Sequence-Defined Structure, a true statement as it relates to DNA? No. No. Doesn't matter what the sequence of bases are in DNA, it's going to make a double helix every time. So last time we talked a little bit about predicting helix location in globular proteins based on, we draw a helical wheel and we look at where the polar and nonpolar groups are located. We can maybe predict where it would be for a water-soluble protein. Okay, so we said if it has a bunch of nonpolar groups, it probably needs to be buried completely in the interior of the hydrophobic core. It wants to stay away from water. Amphipathic, same definition as everything we've been saying. It has polar and nonpolar characteristics. Okay, so it's going to be on the surface, so that one face of it can be to the interior and one face can be to the exterior, and then potentially you could have a totally exposed helix made of primarily all charged or polar groups. Okay. Which one was the most common one in nature? Amphipathic. Okay. Pretty much in globular proteins, this is always a trend. And then I show this slide again. I don't know. Who knows? Who knows what I was going to say? But so we talked a little bit how to predict, I guess, location of helices within a globular protein that's in a water-soluble environment. So if you want to talk about how to predict alpha helices in a hydrophobic or transmembrane region, we could look at a hydrophobicity scale.